Hello everyone, welcome to my presentation on vectorized query processing using Apache Arrow. I gave this talk 2 weeks ago at Strata Data Conference in San Jose. A brief introduction, my name is Siddharth. I'm currently a software engineer at Dremio as part of in-memory query execution team. I'm also a committer for Apache Arrow project. I was previously employed with Oracle as part of database engine team and worked on projects related to storage, indexing, transaction processing, and columnar query execution. I also love writing technical content, so I'm an active technical blogger and contribute a lot of technical content as part of on things that I learn as part of my software engineering job on Quora. So Apache Arrow project. It's a top-level open source project in Apache Software Foundation. It was announced 2 years ago and has seen rapid growth. Developers from 13 plus major open source organizations and projects have been contributing to the growth of Arrow community in terms of code, documentation, evangelizing the project, as well as helping out new users on the mailing list. The main emphasis is on developing data structures in memory format, as well as libraries to support high performance in memory analytics or data warehouse workloads. Arrow has been designed to work with different programming languages like Java, C, C++, JavaScript, and several others, and supports a very flexible data model. You could store like simple or very flat data types and go all the way up to complex nested hierarchical JSON data types. Let's talk about few goals of the Arrow project. So the columnar memory format has become the de facto format for running high-speed analytical workloads or data warehouse queries, which typically focus on a subset of columns, but a large fraction of rows along those columns, like aggregations, joins, or simple scans. Now, the columnar format actually allows the developers to write data processing algorithms for these particular queries in a very CPU efficient and cache conscious manner, and that improves the performance of these queries by an order of magnitude. Secondly, the columnar format allows us to leverage several hardware performance characteristics like single instruction multiple data or SIMD instructions that can further accelerate such workloads. Another aspect or another goal associated with Arrow project is interoperability, where Arrow can actually act as a centralized data format for data exchange between different processing systems. A few more details about this in the coming slides. If you can take Arrow's implementation or the in-memory columnar implementation, the data structures and the library in any language, right? And you can plug that into any other system like Spark or Impala to build a high-performance columnar execution engine. So you can, so these systems can actually leverage the in-memory format as well as the wire format of provided by Arrow and build a very high-performance query execution engine. Thanks to the Arrow community, the documentation around the code as well as the design, the format, and everything is extremely good, and it is cross-language compatible. So we pay a lot of emphasis on verifying compatibility between different implementations, like sending data from Java to C++ or vice versa. So in a nutshell, Arrow is a standardized language-independent columnar format for running analytical operations in a very efficient manner on modern hardware. Let's talk a little bit more about the interoperability aspect of Arrow. So we have different data processing systems like Spark, Impala, Kudu, or Cassandra, and each of these systems have developed their own in-memory format, which are tailor-made to meet their performance requirements as well as functional requirements. But when the time comes for these systems to exchange data, they pay a lot of performance penalty around copying the data, converting and the target memory format, and then serialization and deserialization, and the same set of steps are repeated on the other end. Now, if these systems can be provided with a common format of data, a common in-memory format that each of them can leverage, they can actually avoid all the performance overhead associated with serialization, deserialization, copying, and conversion. So, as far as the cross-system communication is concerned, performance can be improved with a standard data format like Arrow. So that's where Arrow can act as a high performance interface for data exchange. The main emphasis with Arrow is CPU efficiency, basically building data structures and formats for supporting analytical workloads and running them in a highly efficient manner. So the traditional, I'm sorry, so the traditional OLTP workloads, they benefit from the row format. Basically, they benefit from the fact that a single row is stored in a contiguous fashion. A row and all the column values for the row, right? They are stored together in memory or on disk. Now, the data warehouse workloads or the analytical queries, right? They don't benefit from from such format. Columnar format is the right format for such queries because all the values, all the cells for a particular column are stored together again in memory or on disk. And this data structure organization actually allows us to write very simple and efficient code to for query processing algorithms. Like we can write a simple tight for loop code to run through the column values in a very efficient manner, and this kind of code will be very CPU efficient as well as as well as cache efficient, because you'll be filling your cache lines with related data. All of the values in the column are of interest, and what you are loading into CPU registers as well as memory is the data of interest. So you are basically maximizing and utilizing the CPU memory bandwidth in a very efficient manner. Similarly, compiler helps us a lot along with this data format, because such kind of code can possibly be converted into vectorized instructions automatically by compiler if the compiler sees such optimization opportunities during compilation. These opportunities are not available to us when we write query processing algorithms for row-oriented data. Arrow in-memory format for columnar data actually allows us to leverage any, or sorry, access any cell value in the column in a constant manner, in constant time, modulo any structure overhead that we pay upfront to interpret the metadata and other things. Similarly, columnar format also allows us to use CPU efficient compression schemes that are extremely lightweight and actually favor the performance of query rather than actually favoring the compression ratio, which can hurt your CPU efficiency tremendously. More on the compression later in the coming slides. We have two types of data representation in Arrow, for scalars as well as complex. Scalars we have for both fixed width scalars as well as variable width scalars. Like for example, we have representation all the way from short, tiny int, small int to 4-byte int, and then 8-byte big int or long, and then two's complement decimal representation in a 16-byte format, and then 4-byte float, 8-byte double, and multiple different representations for date, time, timestamp, interval to store different kind of resolutions. For variable width data, we have like UTF-8 or varchar as well as var binary, where each value in the column is of variable width in nature and not fixed width, unlike other scalar vectors. And then for complex, we have struct, list, and union, and these can together be combined in an arbitrary fashion to represent any kind of hierarchy or nested data, nested JSON like data. Like for example, you can have a list at the top level, and inside the list you can have scalars, which are the leaves. Like for example, you can have a list of ints, right? Or you can have a list, and inside the list you can have a struct, which is again a complex, but the struct inside can have scalar vectors like int and a float. So you have a list and struct, and the struct is of int and float. So that's how you can actually represent different fields in your data set, different complex fields in your data set into corresponding columnar representation in Arrow. Let's take a few examples to show how we actually translate the data into in-memory columnar representation in our data structures. The first example is for a fixed width 4-byte int vector. Basically, it's a representation for a 4-byte integer column where every value in the cell is fixed width 4-byte in size. There are two buffers to store the column data. The first buffer is a validity buffer, which is basically a bitmap data structure to track which value in the column is null or not. So if the bitmap value is 1, right? If a particular value in the position is 1, the corresponding value in the column is non-null. If it's 0, then the corresponding value in the column is null. The actual column values are actually stored in the data buffer. So the data buffer, each value in the data buffer is fixed with 4 byte in size, storing the actual column data. So in this case, as you can see, the fourth value in the column is null, right? It's in the data buffer. It could be garbage or it could be anything which we don't have to interpret, because the validity buffer the bit is not set over there. So these two buffers actually make up the in-memory representation of int vector to represent any kind of a fixed width 4 byte column. Then we have a variable width representation on the right hand side, where each element in the data buffer is of variable length and size. So along with the validity buffer and the data buffer, we need additional piece of information or metadata to track the start position, end position of each of the elements in the column, right? So we have offset buffer, which is again a fixed width buffer, where each value in the buffer is of 4 byte in size, and offset buffer stores the helps us to find out the length of each value in the variable width column. So in this case, we have two values in the variable width column. The first is SIDD which is 4 bytes in size, and the next value is VAISH, which is 5 bytes in size. So the offset bar, the starting offset is 0, and the next starting offset is 4. So that means the length of the first element in the variable width column is 4 bytes. Then the next starting offset is 9. That means the length of the second variable width element in the column is 5 bytes. Notice the fact that here, although we have two values in the column, the number of positions which have valid data in the offset buffer is actually always one more than the number of uh, column values. This is always true for variable width elements, because we need an additional position to track the last offset. So if you have like 10 values in the column, right, you need to have at least 11 data for 11 positions in the offset buffer. Otherwise, you will not be able to track the end offset of the 10th element in your variable width column. This is not true for fixed width columns, because the validity buffer and the data buffer, they run parallel to each other, and there is no concept of offset buffer. Let's take a slightly more complex example to see how the JSON like data can be represented in an in-memory columnar vectors. So here we have data for two individuals, and for each individual we track information like name, ID, and addresses. Name is again a varchar, so it can be represented using three buffers like validity, offset, and the data buffer, as mentioned in the previous slide. Then ID is again a fixed width column, so it can be represented like fixed width 4 byte int vector, as again mentioned in the previous slide. The most interesting piece of information over here are the addresses. So each person can have one or more addresses, so which indicates that addresses at the very top is a list, some form of a list, right? So the first person has one list because it has one address. The second person has two lists, right? Two elements in the list. Sorry about that. So the first person has one element in the list, and the second person has two elements in the list. And the internal pieces of information inside the list are number and street, which is which form the address information. Inside the list we have struct, and inside the struct we track these two members, which is a number and a street. So that's how we represent this data in a hierarchical fashion. We start with a list, each and the list has a struct, and the struct has then has scalars, number and the varchar. Now let's see how we actually retrieve the information for each of the address information for each of these individuals from the list vector. At the very top, the list vector has an offset buffer. The offset buffer indicates the number of elements in the list at each position. So in this case, at the first position we have only the number of lists are one, right? Because the first person has one address. In the second case, the number of the size is 2, right? Because it has two different elements in the list, right? The first address and the second address. So the offset buffer helps us to track this. If you take the first element, the start offset is 0, the next offset is 1. That means the size is 1. Now we use this information to make a call to the internal vector, and the internal vector in this case is a struct vector. So what we typically do is do a struct vector dot get object 0, right, at position 0. and the struct vector delegates the call to internal vectors, which in this case happens to be an int vector as well as a varchar vector. So then the call goes to int vector.get 0, right? And the answer is 2, which gets the number information for first person, right? Then you do varchar vector.get 0, right? And in this case, because it's a varchar vector, so we again have to go down to the offset buffer of the varchar vector, which tells us that, hey, at the first position, the 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 length of the variable width field is 1 byte, which is a. So that's how you get the address information for the first person, and you know that this is the only first and the last address because of the offset buffer, because it indicated a size of 1. In the next case, you say the first start offset is 1 and the end offset is 3, right? So that means the size is 2. So that here we'll make two different calls to struct vector. We'll do struct vector dot get object 1, and then we'll do struct vector dot get object 2. And that way we can actually retrieve two different pieces of information uh, for the address. So we'll do int vector to get object 1, which is 4, and then varchar vector dot get object 1. Here we'll find out that the length is 2 bytes because the start offset is 1 and the end offset is 3. So we get information as CC. So the first address information becomes 4 and then CC. And then we do struct vector dot get object 2. So then we get int, get the element in the int vector position 2, which is 5. Then do the same thing for the varchar vector. Here we find out that the length of the variable width field is at that particular position is 3 bytes, DDD. So we get the information as number as 5 and street as DDD, and this forms the second address for that individual. Moving on to arrow messaging. Basically, every arrow message is responsible for sending enough information over the wire such that at the other end we can decode it completely and reconstruct the table data in memory into arrow vectors, or each vector is a represent in memory representation for a column in your data set, a column or a field in your data set. So schema basically consists some kind of a metadata describing each of those fields or columns, right? So a typical arrow message starts with a schema having all the metadata describing each of the columns in your data set. Now you can choose to encode some columns, one or more columns in your data set with dictionary encoding scheme. So if that is the case, then immediately after the schema, we'll have the dictionary. So in this case, the actual data, that actual table data is one column, and that one column is A, B, C, B, A, C, B, basically a char column, right? And if the field is dictionary encoded, then after the schema we'll send a dictionary batch having the entire dictionary for the values. So the value A in the column is encoded with dictionary value 0, value B in the column is encoded with value 1, and C with 2. So after the schema we send the we add the dictionary batch to the message, and after the dictionary batch we have the actual record batch, where in this case the record batch will be referencing the dictionary values that were a part of the dictionary batch preceding the record batch, and the schema dictionary batch along with the record batch forms a complete a single arrow message. If there is no dictionary batch, that means there are no fields dictionary encoded in your data set. So after the schema, immediately there will be one or more record batches. We support both streaming format as well as file format for arrow messaging, and both these formats have support for randomly accessing any record batch in the stream. A streaming format or file format are basically similar. It's just that in the streaming format you can look at it as a sequence of encapsulated messages. So you at the beginning of a message you have some metadata, and the length of the metadata, which is a fixed width 4 byte, and then so you get the length, and then you get the metadata and then read the message. Then again, and then you do the same thing for the next message in the stream. So that's how you can actually implement a streaming reader for arrow messages. This particular slide describes how we construct a record batch when we have to send the table data over the wire. So it basically is an enlarged form of the record batches that we have shown on this slide, like what goes inside a record batch. Record batch is nothing but basically the actual data for the different columns or fields in your data set, right? At the end of the day, what we are sending over the wire is the table data. Now here the table data representation is in the form of arrow vectors. So for each column in a data set, we have an in-memory arrow vector, right? And the vector stores the data in form in one or more buffers, right? So in this case, if the data is name, age, and then phones, then for the name column we have three buffers because it's like a varchar vector, right? So we have the validity buffer, the offset buffer, and the data buffer, and each of those buffers become the part of the record batch that we are sending over the wire. Then we add the buffers for the age column, which is the validity buffer and the data buffer. And then similarly we do the phones thing. So what we are sending over the wire is essentially the information that makes up the data set. Now for the guy on the other side to be able to reconstruct a record batch in memory in the form of arrow vectors for each field, right, we need some metadata, like what are the length of these buffers, right, how many null values are there in each column, right, and all of this information is encapsulated inside the data header. And we also send the these addresses of these buffers because each of these buffers is a physical contiguous chunk of memory. So the validity buffer is a contiguous chunk of memory for name, and the offset buffer for name column is a contiguous chunk of memory, the data buffer for name column is a contiguous chunk of memory, and so on and so forth. So it's basically a contiguous chunk of memory related to any address space, which could be a memory mapped file, or it could be anything. And and this allows the entity on the other side to be able to construct a record batch in memory without any copy. So it's so with arrow messaging we support zero copy deserialization and serialization, that actually provides very fast data access. When we are working with complex or nested data types and trying to form the record batch for serializing over the wire, what we essentially do is that we traverse the tree in a depth first manner, literally flattening the tree, visiting each node, getting the metadata and the data and the information about the buffers at that level, and then just adding them to the record batch. So it's like looking at the tree or the vector tree for a typical representation of hierarchical data, and then just flattening it out, and adding the data and the metadata to the record batch. Because whichever way you look at it, whether it's simple data or complex data, right, the data is stored in some vectors, and those vectors store the data in some physical buffers, one or more buffers, right, and each buffer is a contiguous chunk of memory. So what goes over the wire is basically this information. Arrow supports different language bindings, with the main goal being cross-language compatible. We currently have strong implementations for Java, C++, C, Ruby, Python, and JavaScript, and there are several other languages implementations in pipeline like R, Julia, Go. The next set of slides will focus on how we have leveraged Arrow libraries, its data structures, and columnar in memory format to build a high performance in memory execution engine in Dremio. Dremio is a data platform to support to accelerate the, the data warehouse or analytical workloads across heterogeneous data formats. It's basically a self-service data platform. Our core execution engine is called as Sabo, and it's built entirely on top of Arrow libraries. It's is in-memory columnar format, it's wire format, and is written entirely in Java. So we'll talk about a few aspects of related to the usage of Arrow inside Dremio, like memory management, and then majority of the slides would be focused on vectorized query processing, talking about some details with respect to the design and implementation of some of our vectorized operators like hash aggregation, vectorized copy, a few details about how to use compression with respect to columnar data, and few details regarding the implementation of our vectorized Parquet reader. So let's talk about the memory management inside Dremio with respect to Arrow. Arrow actually includes a chunk-based managed allocator, which is built entirely on top of NetEase JMalloc implementation. The main memory management model or allocation model is a sort of a tree-based model. I'm sorry, where we start with a root allocator, and the root allocator then internally has different child allocators created for different pieces of work. And one of the important semantics that we enforce at the allocator is some sort of a initial reservation and limit. So when you create a child allocator, by creation I'm not meaning that allocation of memory. It's merely creating an allocator object or instantiating the object. You can impose a reservation that, hey, this allocator in future should be able to allocate this much of memory safely, and this much amount of memory will never be released or given to the parent allocator until the allocator is closed. So this is for the initial reservation semantic, right? That hey, I'm safe. This much of memory I should be allocated in future. I don't want to allocate it upfront, but I should be able to allocate in the future if there is a need. And then there is a memory limit. Now, memory limit in generally in systems could be a limit that is imposed by the operating system, or it could be a limit imposed by the JVM. In this particular case, we are imposing the limits ourselves locally inside the application. So each child allocator or each allocator has a limit on how much of memory it can allocate during its lifetime, and it cannot go beyond that. So even if you set an arbitrary limit on some child allocator, is it is bound to never go beyond the limits set on the parent allocator. So we use reference of buffer management. Basically, all the memory that comes for storing the data inside our in-memory columnar vectors uh, comes from direct memory. It doesn't come from the JVM heap to save ourselves from some overhead associated with garbage collection in Java. Now let's talk about a little bit in how we use these tree-based allocation model as well as the initial reservation and memory limit semantics inside Dremio. So each operator in the query plan tree gets its own allocator. So you have, let's say you have a query plan of say 8 operators. I don't know, some random number. Each operator will get its own allocator with some initial reservation and memory limit. Let's take the example of external sort operator, which is the operator responsible for handling the sort queries with the ability to sort large amounts of data sets and gracefully handling the out of memory conditions, and because it has the ability to spill data whenever we are running under low memory conditions. So at the top level we have a root allocator for the operator, right? When we set up the operator and the operator execution has to begin, it gets its allocator. There are two main subcomponents of the sort operator. One is the memory run, and the second is disk run. Memory run is basically responsible for as the incoming batches of data are arriving into the operator, it keeps sorting them in memory and adding them. So basically, if the life is good, you never run out of memory. What happens is that data keeps arriving into the operator, keeps getting sorted, and nothing happens. At the end, when the input, all the input has been processed, you have all the data sorted, and the operator can start outputting the data out of the memory run subcomponent. Right? We also have a disk run component which manages the spilling. So in case we run out of memory, we need to spill the in-memory data which is already sorted. And then once the data has been spilled, we again need to do some sort of processing to load that data into memory, continue with some sort of merge sort, or load different streams of data into memory and do some sort of n-way merge in memory and sort the data, finally finish processing and then pump the data out of the operator. But this doesn't happen in a straightforward manner, because let's say you are adding data, the memory run is adding data as it is arriving into the operator and sorting them. Now, if in future you run out of memory, you need to spill, right? And the act of spilling might itself require some memory because you need to copy the data out and then spill it, right? So what memory run does it in order to guarantee 100% spill is that as the incoming batches of data are arriving, right, we know the size of the data because we keep a track of what kind of data types or fields we are working with. So it kind of maintains a running maximum of different of the size of the batch that has been arrived, right? So each unit of work given to the operator as input is a batch, a data batch of some number of records, right? And memory run keeps track of the largest batch that has been added so far and uses this size to update its initial reservation of the child allocator. Now, how does this help? This helps because in future, if there is a need to spill, the child allocator provided by memory run has the ability to allocate enough memory to copy out the largest sorted data batch from memory and spill to disk, right? So that's how the initial reservation semantics with memory run help us. in a very real world scenario. Now, once you have spilled the data to disk, the problem is not over, because even though let's say you ran out of memory, you spill the data disk, oh, life is good. No, because now you need to make sure that you have enough memory to load the data back into disk and finish your processing. So that's what disk run child allocator does. Again, this child allocator is created of the top root allocator and the sort operator. And what this does is that it keeps a track of how many times we have spilled data to disk. Times as in like the number of spill iterations we have done. And in each iteration, we spill the data in terms of multiple chunks, like multiple bite-sized chunks. So in a single iteration, we may have spilled like 10 chunks, and then each chunk would have a size that went to disk, right? So this guy keeps a track of each such iteration and the largest chunk size spilled per iteration. Now what it has to do is to, in order to do an n-way merge of data loaded back into memory, it has to be able to allocate memory equal to the amount of the largest batch size, largest chunk size spilled per iteration. So let's say you have had 3 or 4 spill iterations, right? And in each spill iteration, we spilled 10 chunks of data. And let's say the largest chunk size spilled per iteration was W for first iteration, X, Y, Z for second, third, fourth iteration respectively. Now in order to do a 4-way merge, right, of 4 chunks from each of these iterations, we need to be able to reserve a memory, minimum memory equivalent to W plus X plus Y plus Z plus some constant to, for additional safety. So this is how we use these memory reservation, the tree-based model, and different semantics to implement an operator that can handle out-of-memory conditions in a graceful manner. A little bit more about the memory management. In Dremio, the data flows through in a pipeline fashion. So it flows from one operator to another operator as a set of vectors. Now we call it a record batch. In this case, we have shown 2 operators, scan and aggregation. And the data set happens to have 3 columns, and it has one arrow vector for each of those columns. So you have 3 vectors. A scan operator has done the processing, and has and now that the data has done some processing, right? And now the data batch has to be fed into the aggregation operator so that it can start the processing. Typical SQL processing: one in the output of one operator becomes the input of another operator. Now remember, in the previous slide I mentioned that each operator gets its own allocator. Now here we are not doing any copy here, right? We are simply transferring the accounting and ownership business for that particular data batch and vectors to the allocator of aggregation operator. The scan allocator has done its job, releases its control and claim on the memory associated with the data batch and these vectors. Now we use the transfer capability that is implemented as part of each vector to just transfer the control, the memory ownership and accounting responsibility of the buffers for each of those 3 vectors to the allocator of the aggregation operator. And there is no data copy effectively needed. It's just that control is now with the aggregation operator of the record batch. Sorry. Moving on to vectorized execution. So there are typically 2 models of query execution that are generally mentioned in literature or text for database design and implementation. The traditional model is also called as an iterator model or a tuple-based model. So each operator in the query plan tree pushes one tuple at a time up the tree. So you have operator at the bottom, scan, it starts processing the data, and then pushing the data up in the operator tree one tuple at a time, right? And then there is another model which is called as vectorized model. Now there are 2 differences here. First, the focus has completely shifted from writing query processing algorithms for row-oriented data to vectorize to columnar data format, right? So you have columnar representations, wherein one column is stored in a contiguous fashion, and a vector, and the in-memory representation is called as a vector containing fixed number of values from the column. The second difference between the vectorized model and the traditional model is that instead of pushing one tuple at a time up the query plan tree, We basically push a block. A block comprises of different tuples, and then those tuples are stored as a set of vectors, right? So you may have like a block may comprise of 4,000 tuples or 4,000 records, and they are stored as vectors in a columnar representation, right? It's kind of a block of vectors, and this is the unit of data that is transported from one operator to another operator as the query execution progresses through the query plan tree. Now there are several benefits of such kind of processing. Firstly, when we load the data from disk, right, a single query needs to touch the columns only that are required by the query, because the data is stored in a columnar format. So you save a lot on the disk IO bandwidth by just touching the columns that are necessary. The similar theory is applied when you actually process the data in memory and load into CPU. You are filling your cache lines with related data because each column is stored together. All the values in the column are of interest, right? You whatever processing you need to do, you can write a simple tight for loop and run through the column values in a very efficient manner, doing filter out the column values, add the column values with another column, and this code is going to be far more efficient than loading one tuple at a time, and the tuple might have 100 columns and only one column out of that might be interest. So you are populating the cache with unnecessary data, and that's why such code is very less CPU efficient. Let's take the example. On the left hand side, we have the traditional model of the tuple at a time. So the scan operator starts getting the input data, right, and starts pushing tuples through the filter operator. And then the filter operator then pushes the qualifying tuples to the aggregation operator, right? And the operator keeps calling next on the operator downstream in the query plan tree. Sorry. And the output of that is that the operator down in the tree starts pushing the tuple up to the operator located above in the tree, and that's how the query execution proceeds. Now there is severe performance overhead in this execution because uh, just look at the number of function calls that will be there, right? And the poor utilization of the disk bandwidth as well as the CPU memory bandwidth, and also about uh, the efficiency associated with the usage of CPU cache. You are transporting a tuple, whereas you may need to work only with a set of columns in that tuple. So this is definitely a poor way of processing, writing query processing algorithm, especially for data warehouse workloads. On the right hand side, now we have, instead of pushing a tuple at a time through the query plan tree, we are pushing a block of vectors. Each vector has a set of records or fixed number of records or column values, right? And there are as many vectors as there are columns in the data set, and you just keep pushing a batch of these vectors up the query plan tree, and this will be the input and output of different operators in the query plan. This approach is far more efficient than the other approach because uh, you optimize or you amortize the cost associated with function calls between different operators like next, right? You're not pushing like a million tuples of the tree. You're just reducing the cost by many fold, right? Let's talk about how we actually size our vectors. So as I said, I think I've said this, I've mentioned this multiple times in the presentation without explaining it, is that a unit of work in Dremio is called as a record batch or data batch, or a set which comprises of arrow in memory vectors. Each vector is for a field or a column in your data set and consists of a fixed number of records. So let's say you have like a million record data set. What we will work on at a time is like a record batch of 4,000 records, and this is the record batch. This record batch is also the unit of data that flows through the pipeline or the query plan tree from one operator to another operator. Now there are different kind of mechanics associated with how do we fix the number of records in a data batch. So it could be like 1 or all the way up to 64,000. We have seen that the large batch size like 8,000 or 16,000 actually improves the performance because the unit of the unit of work increases, and the number of times you'll repeat the processing goes down. But the larger batch also causes pipelining problems because you are actually sending extremely large amounts of data between one operator to the another operator. Whereas if you use a smaller batch size like 128 or 256, right? Although the processing on an individual batch will be faster, and then the amount of data transferred between the operators is going to be much slower. But because of the sheer number of times that the processing has to be repeated and the volume of objects that will be constructed, the heap overhead of a query just shoots up. And that's why the standard record batch size that we have been working with in Dremio and that is configurable is record batch size of 4095 records. Now there is an interesting reason why we do not use a power of 2, something as 4096, but we use a power of 2 minus 1, 4095. Because remember that for for vectors which use an offset buffer like a variable width vector or a list vector, the number of valid data positions in the vector are always in the offset buffer are always one more than the number of actual values in the column. So if we use 4096 record, that means 4096 column values, we will actually end up allocating the offset buffer for 8192 records because of power of 2 allocation semantics in Arrow. So that's why we use power of 2 minus 1 number of actual column values, and that way we will not over allocate the memory required for the offset buffer. Instead, we will just allocate memory required for offset buffer for this 4096 values, which is exactly what we need. With batch size, we actually control the amount of memory that we have allocated for the vectors. So in operators like external sort or aggregation or join, where we really need to be conscious of the amount of memory that the, that the operator has reserved, then the amount of memory that each child allocator has to work with. We cannot really be allocate memory for vectors without being aware of what is the default memory allocation. So you cannot do just vector.allocate and leave it to the API to allocate some default memory, because at the end of it you can run out of memory because you were supposed to work within certain memory requirements. So carefully configuring the batch size and the number of vectors, number of values in the column vector, right? And then allocating memory appropriately just for that, just for those number of records, allows us to write our algorithms which are very graceful and are very robust. Let's take an example of on how the vectorized query execution leverages SIMD acceleration to further improve the performance of analytical queries. So we have data for a simple column, and let's say it's just a fixed width column where we have a validity buffer as well as the data buffer. So in a single SIMD load instruction, we load the data into a 128-bit SIMD register. I'm just taking an example of SSE2 SIMD, a 128-bit register, although modern Intel processors are equipped with AVX 512-bit SIMD register. But let's just, for the brevity, let's just take this example. Each value in the column is 4 bytes in size. That means in the single SIMD load instruction, you can load 4 values from the column into the register, right? Now, in a single comparison instruction, you can do a filter processing. So in a single SIMD instruction, yeah, you can leverage data level parallelism and find out which of these 4 values are greater than or equal to 100. So you can do extremely fast predicate evaluation by using SIMD instruction on columnar values. The output of this SIMD evaluation is kind of a bit mask or element mask. It's like basically each value is a 32-bit integer, either all ones or all zeros, indicating which column value uh, pass the filter or pass the predicate or not. So in this case, the first, second, and fourth value pass the filter. But again, we now need to find out which of these are null or non-null, and then finally construct the output. So we then take the validity buffer in a single SIMD uh, instruction. We load that validity buffer into the SIMD register, right? And then again flatten it or expand it such that each value is either all ones or all zeros, and then do a single SIMD AND instruction to just do a logical bitwise AND of all the values in the as the output of the predicate evaluation with the validity bits to find out which are the non-null values here. So at the end, what you get is 100, and then you get 120 as the answer, because even though 200 passed the filter, right, in the first SIMD instruction, the second SIMD instruction will give it 0. Now this output can then be fed into a branch free for loop, a very simple for loop, and we can just do some bit shifting on that and then construct the output vector. So there are no branches needed. It's going to be extremely fast. So this is how SIMD instructions can be used in a very simple manner on columnar data to accelerate the processing by an order of magnitude, especially for operations like scan, filter, sum, and other operations. These can be accelerated by an order of magnitude by using SIMD instructions. Let's talk about a few details of design and implementation of our hash aggregation operator. So in our performance experiments, we figured that if we use a columnar format for looking up the hash table or inserting data into the hash table, it is actually not very efficient. So yes, until now I have talked about that yes, we need to have columnar format for such and such reasons to suit the performance requirements of these workloads. But yes, there are cases where the performance uh, is not is kind of suboptimal. So what we do is that even though the overall implementation of the operator is vectorized, the hash table actually stores the group by key column data in a row-wise format. So we get the input data batch in vectors columnar format. The input data batch for hash aggregation comprises of two types of columns. One set of columns is the group by key columns on which you are doing group by on. The other columns is the aggregation columns like sum, like salary, sum, average, min, max, count, right? The aggregation columns. These are, and all of these columns in the data batch, input data batch, are in columnar format. It's the record batch basically of the operator, right? So what we do is that we do first, let's just talk about the group by key columns. Because we discovered that storing them in columnar format is going to hurt our performances, so we first pivot them into a row-wise representation. So the hash table is broken into two regions. One is the fixed width continuous region. The second is the variable width contiguous region. The fixed width contiguous region stores the row-wise representation of all the group by column keys, the fixed width keys. And the variable width contiguous region stores the row-wise representation of all the variable width group by key columns. So we get the input data batch, pivot the columnar data into pivot space, which gives you a row-wise representation. Then use the row-wise representation or the linearized array of bytes to compute the hash on the entire batch of data. We write a simple for loop, compute the hash on the entire batch of data, and then just loop over them and insert the keys into the hash table. The aggregation columns like sum, min, max, right, and the corresponding columns, they are always represented in columnar format. So what we do for them is that we form a vector pair. The input vector, which is given to us as part of the input record batch, and the output vector. Output vector will store the computed values. Like if you have the input vector as a salary and the aggregation that you want to do is sum, then the input vector will be the salary column, actual column, and the output vector will store the computed values, the summation values for each of the unique keys that are given to us in the group by key columns. And at the time of projection, the output vector can be directly projected into the result set that's pumped out of the operator. Now this output vector in the aggregation column is related and associated with the hash table data structure, because once we insert the row-wise keys row-wise keys into the hash table and we get an ordinal is basically an insertion point into the hash table. We use a fixed set of bits from that ordinal to determine the address into the output vector of the aggregation to go and accumulate the value, right? So if you have a fixed width key, let's say you have a fixed width key as age, right, value 25, and then you have a variable width key something, I don't know, some text, right? That forms a one row wise key. You compute the hash on it, you insert that into the table, and then you get an ordinal. You use some bits from the ordinal to figure out what is the value in the input vector, what is the corresponding salary for this group by key, and then where to store the summation of the salary into the output vector. So that's how these data structure, the row-wise representation of the keys and the columnar representation of aggregation columns are connected together to build a high performance hash aggregation algorithm. A few more details. You get an input batch. The input batch is comprising of three vectors here. First, pivot. So basically, by pivoting IC, you can see different rows. So you pivot into row-wise format, whereas you have all the fixed width columns, and then you also indicate with which value in the column is validity or not. Similarly, you have the variable width columns, because variable width columns you need to track the length of the each column. So each variable width column is then preceded by the each variable width column data is preceded by the length of that particular data. Again, everything is in a row-wise fashion. You compute the hash on this, insert into the hash table, and then use the hash table insertion ordinal to build your aggregation tables, which are columnar format. Once the entire input data has been processed, you unpivot. That means you basically unpivot the row-wise representation from the fixed block region and the variable block region in the hash table to their corresponding columnar representation of the group by keys. Because what hash table has is the unique group by keys, right? It's just that they are in row-wise fashion for performance reasons. Unpivot, uh, construct columnar vectors, and then directly project the computed values from the output vector in aggregation columns, and then that makes your output result set for the hash aggregation operator. Let's talk about vectorized copy. In several cases or several pieces of code in Dremio, we copy records between input and output record batches. There are typically two kinds of copiers. The first is a straight copier, where we simply leverage the transfer capability we have implemented over each vector, where we simply transfer the memory accounting and ownership business from an allocator of one operator to an allocator of another operator without really copying the memory physically. So we just use vector to vector transfer. Okay, vector v1, this buffer, your memory ownership is now to vector v1's another buffer for a different allocator. So it's just that you transfer the data batch, and that makes a straight copy. The another copy is when you want to actually copy a specific set of records in no specific order from an input column vector into an output column vector. Now here we use an additional pieces of information, something called as a selection vector data structure. And there are two kinds of selection vector data structure, it's 2 byte and 4 byte. Let's talk about the 2 bytes data structure. That we use the 2 byte offset to index the input column, like which value in the column needs to be copied, and then get the source data for the copy, and then use this to copy into the output vector. And all of this code is written in a very C++ style. It's a simple for loop where we directly work with the underlying chunk of memory. We bypass the entire arrow vector APIs, the function calls associated with them, and just directly work with the memory uh, used underneath by the vectors. And then just simply keep shifting the address window, use the selection vector, the 2 byte offset, to index the input vector data buffer, get the address, and then get the target address, and then do a simple mem copy using the APIs provided by platform dependent. So this way we implement a highly efficient vectorized copy of different types, both doing a straight copy in which we just transfer the memory accounting and ownership business from one allocator to another allocator, and the second copy in which case we actually do copy specific cell values from one column to another column in a very efficient manner. Columnar format actually allows us to leverage very lightweight and CPU efficient compression schemes, like general purpose compression schemes, which are used heavily in databases and other systems like LZO and zlib. They give you a phenomenal compression ratio, but they hurt CPU efficiency because the cost of compressing the data and decompressing the data adds up to the query execution time. For columnar data, the focus is always on building high performance query processing algorithms. So the focus is on performance and the minimizing the runtime execution time of the query. But that doesn't mean we will not use compression. It just means that we have to find other optimal overheads. So columnar format allows us to use several lightweight schemes like dictionary encoding, bit packing, run length encoding, where there is absolutely to no CPU overhead of using these schemes. And secondly, they actually in some cases they allow us to directly operate on the compressed columnar data, and that improves the performance of your queries by an order of magnitude because you don't have to decompress all the column data upfront before starting the processing. Like for example, you need to do some, you have a scalar column, you have variable width column, right? Now variable width column, generally you cannot do SIMD on that, right? But because SIMD needs like a fixed alignment to for the values of the column to be loaded into a SIMD register in a single instruction. But you can use dictionary coding compression scheme to encode your variable width column values into fixed width dictionary values, and then write your query processing algorithm on top of the dictionary values. So that way you are, instead of working on the actual variable with non-compressed column values, you are working on fixed width dictionary encoded values. And we can use different types of information about a column, like what is the cardinality of column, whether the column is sorted or not, what is the data type. Like for example, if the column has a low cardinality, right, we can generally use dictionary encoding, because we also do not want to want to waste a large amount of memory on building the dictionary. So that's why low cardinality columns are favorable for using dictionary compression scheme. Similarly, if you have like lots of repeated data values, right, like 40 40 40 40 40 and then so on and so forth, right, you can use a simple scheme like run length encoding to just convert this data from simple column values into triplets. Like the data is 40 starting offset and the run length, like how many times the data is repeated. Let's take an example on using the how we use dictionary encoding on the variable width column values. So you have column values which the unique column values are United States, China, India, France, United Kingdom, right, which are variable width in nature. And you need to write a query which does a filtering on that or a predicate evaluation on that. So what we do is that we dictionary encode this column, and on the left hand side we show the dictionary values, right? And on the right hand side we show the encoded values in column using the dictionary. The query comes as the select something from the table where country is equal to France. Now we use France to consult the dictionary and get the dictionary encoded value, which is 4. We then load 4 in a single SIMD instruction into a SIMD register. We load all the encoded column values, uh, the dictionary encoded column values in a single SIMD instruction into a SIMD register, right? Like you have loaded all the 254317 values in a SIMD register, and just do a parallel predicate evaluation or parallel compare in a single SIMD instruction. So this way you can actually rewrite, as I mentioned in my previous slide, the rewrite filter on strings as filter on fixed width dictionary values. And this is the power of dictionary encoding. You can actually compress your variable width column values into fixed width dense arrays, and then rewrite your query processing algorithms that can just quickly loop through those compressed column values in a very efficient manner. So directly operating on compressed data, you are decompressing only the necessary data, right? So Dremio uses materialized views to cache information, basically the information that can be used to accelerate subsequent queries or queries in the future. And those materialized views are stored in columnar format on disk. We leverage the Parquet's columnar format. But when we have to run a query and then materialized view has to be used for the query, we load the data from columnar format on disk in Parquet to the corresponding columnar format in memory into Arrow. And our initial reader for this was actually based on a row oriented format. It was basically a row wise reader, where it was not at all taking advantage of the fact that the source data on disk is also columnar in fashion, and the target data that we are trying to build in memory is also columnar fashion. So then we rewrote our the algorithm, the reader algorithm, to be completely vectorized, where the processing is done one column at a time, and then it is highly efficient because we can completely take advantage of what are the compression schemes that we have used in Parquet for each column, and sometimes even do a bulk copy by decoding those compression schemes in an efficient manner, and then reading each column based on the way it has been compressed into a Parquet page. So now the new reader does columnar operations while reading and writing Parquet files, and we also support filter push down for Parquet scans. So the predicates or the filters indicated in the query can directly be pushed down to the Parquet files, such that we only load the necessary column data into memory when reconstructing the arrow in memory vectors. Let's talk about late materialization. So the main idea is to work on the columnar format till late in the query plan. Yes, I've been suggesting that why storing data in a columnar format is essential to building high-performance analytical query engines. But the idea is not to just read the columnar data and stitch the values together to perform row store operations on tuples. The idea is to keep the columnar format till very late in the plan and avoid constructing tuples only when necessary. This actually improves the utilization of memory bandwidth because you can keep operating on the columnar format as long as necessary, right? Like do filter processing, scans on one column at a time in simple efficient for loops, right? You can even use SIMD processing by when operating on a particular column. Whereas if you do not do this, right, and if you construct tuples upfront, right, you lose the opportunity of using SIMD acceleration. Similarly, when you are constructing tuples upfront, you have to decompress all the values, and you may not have even needed those values, right? So you are actually forming unnecessary tuples. With late materialization, you keep operating on the columnar format till as late as possible. You get several advantages. You can keep operating on compressed columnar data, of course, if it allows. Like for example, like dictionary encoding allows us to operate on fixed width and variable width compressed columnar data, right? You can keep doing that, and you can form the tuples only when unnecessary, right? So you decompress only the necessary data values. This saves a lot of improves a lot on the utilization of memory bandwidth. It says secondly, when you do this, you have to use some intermediary data structures. Like for example, the query is like filter on one column and then project another column. Now one way to do this is that you read both the columns, stitch the values together, form tuples, and then start feeding into your operator, right? But that is very less efficient because you just need to do filter processing on one operator and you need to just project the other operator. So why not just keep the filter column in a columnar format, write process them very quickly, construct an intermediary list or a selection vector to find out which of the values pass the filter, and then use those in that intermediary list to then process the target column for projection and then project the necessary values. So you never constructed unnecessary tuples. You you potentially operated on compressed columnar data. You potentially had the opportunity to leverage SIMD, and then finally you only projected the necessary values. You never formed any tuples. You only formed the necessary tuples. So late materialization, along with the ability to directly operate on compressed data, the opportunity to use SIMD at appropriate points, heavily improves the utilization of memory bandwidth as well as the performance of our queries. Let's talk about how arrow in memory format allows us to unnest list vectors. So there are some cases in which we want to unroll the list to separate records in the data set. So you have a list of several different records. The list vector has an inner vector, and the inner vector could again be a complex vector or a scalar vector. In this case, the list vector has a struct vector, and the struct vector has three scalars inside the inner vectors, right? The memory representation and the data structure format is such that we literally don't have to do any data copy over here. Each vector has been provided with the ability of doing a split and transfer, where a set of records from the vector can be quickly copied or transferred. I would say that the transferred to another set of records in a different vector. So what we are doing over here is that we work on each of the buffers for the inner vector. mm, Node form a slice like the start point of split and the length of the split, and just do a buffer transfer to the target allocator of another vector. And this does a very efficient unnesting of values from the list into separate different records as different vectors. That's it. Please try to get involved with the Arrow community. We have a Slack channel, and then please follow us on Twitter. These are my handles. These are the handles for Apache Arrow, the Dremio HQ, and myself. Also, please join the Arrow community, the Dremio community. Uh, Go to our link on GitHub, sign up for the community edition, and start playing around. Thank you.